In this module, we will learn about linear momentum. Linear momentum is defined as the product of mass and velocity. P equals mv. The symbol P stands for linear momentum. Momentum is a vector quantity. It has the units of kg meter per second. So from the relationship P equals mv, you can immediately see the more massive an object is, the higher is its momentum. Also, if the object is traveling at a higher velocity, then the momentum is also larger. So the linear momentum is directly related to Newton's second law. If you start from F equals ma, and instead of a, you can write dv over dt, which is the time derivative of velocity. And so you have, and since mass is a constant, you can pull it inside the derivative as shown in this equation. So you have dmv over dt, which can also be written as dp over dt. So F equals ma is equivalent to F equals dp over dt, the time rate of change of momentum. That means when you apply a force, you are changing the momentum of an object or a system. If there is no force applied, then the momentum remains constant. In this case, at any instant of time, the momentum is constant. So you can evaluate the momentum at two instances of time, and this gives us a conservation law called the conservation of linear momentum. And this is a very powerful technique to analyze or solve a variety of problems, such as problems involving different particles colliding with each other. For example, you can think of the game of pool. For example, all the different balls in the table, they are colliding with each other and moving with different velocities. Right? So you can apply the conservation of linear momentum to this problem. For example, let me go into a bit of details. So for example, initially when I'm starting the game, I'm using the Q stick to hit the white ball, right? So at that time, momentum conservation does not hold because I am applying a force to the white ball. But once the white ball starts moving, then you can treat the collection of particles as a system and evaluate their momentum. So when all the other balls are stationary, but the white ball is traveling, the system has a certain momentum given by the mass of the white ball times its velocity. All the other balls are stationary. Now, when the white ball hits all the other balls and they move in different directions, the system is very complicated, but the total momentum of all the particles together is still constant because there is no external force acting on the system. So you can evaluate the momentum of each of these balls, for example, given by their masses and their velocity, product of their mass and velocity. And if you sum up all their momentum, then you will see that that momentum is equal to the initial momentum of the white ball, basically. So this type of problems you can analyze by using the law of conservation of linear momentum. But remember, for this law to be applied, there should not be any force applied to the system. Only when the applied force is zero, then this law holds. And so you will be analyzing a lot of collision problems, and there are mainly two types of collision problems that we will be looking at. They are called elastic and inelastic collisions. In both of these collisions, like linear momentum, conservation of momentum will hold because we will assume there will not be any external force acting on the system. But in elastic collisions, kinetic energy, the energy associated with the translational motion of particles, kinetic energy is also conserved. So between the two instances of time, if you evaluate the initial kinetic energy and the final kinetic energy, you will find that they are equal. So there is no kinetic energy loss in the total system. And usually perfectly elastic collisions where kinetic energy is also conserved happens at the microscopic level. For example, electrons colliding with, electrons are subatomic particles colliding with each other. At the microscopic levels, collisions are not perfectly elastic, but some collisions come close to nearly elastic, being nearly elastic, for example. And in some problems, we will assume elastic collisions, but it will be specified. So the other type of collision is inelastic collision, when the initial kinetic energy is not equal to the final kinetic energy. So some energy is lost in other forms like heat or sound, for example. But remember, in both of these collisions, momentum is always constant. So you can write the initial momentum of the total of the system, and it will be equal to the final momentum of the system. And there is a special case that sometimes problems look at. It's called a completely inelastic collision. This is a case when the particles after collision stick together and move together with the same velocity. You may encounter problems like this when you are solving your homework problems or going through the tutorials. And over here, I show a sample problem. It's a one-dimensional collision problem. Two particles colliding. For simplicity, we assume that one of the particle is at rest with a v2i equals 0, its velocity being 0. And the other particle is coming in, other particle of mass m1 coming in and striking this stationary particle with an initial velocity of v1i. And after the collision, both particles move with different velocities v1f and v2f as shown in the figure. And we assume that this is an elastic collision, so we can write down conservation of linear momentum and conservation of kinetic energy. For example, initially the total momentum of the system is m1 times v1i, and after the collision, the total momentum of the system is m1 times v1f plus m2 times v2f. This is the conservation of momentum. And kinetic energy is given by half m times v square. V is the speed. Kinetic energy is a scalar quantity. And so you can also write the initial kinetic energy as half m1 v1i square, because the other particle did not have any velocity. And the final velocity of the system is the sum of the final kinetic energy of the system is the sum of the individual kinetic energies after collision, half m1 v1f square plus half m2 v2f square. So with these two equations, you can solve for some of the unknowns that the problem is asking you about. So let us look at a case where where it is completely inelastic collision. That means the bodies stick together after collision and move with a single velocity. So similarly, the two particles, one at rest, the other coming in and colliding with a velocity v1i, and the final velocity is denoted by this capital V in this equation. And the conservation of momentum gives us this equation m1 times v1i, and this is equal to the final momentum, which is equal to m1 plus m2, the two masses are sticking together, times their velocity v. They just have one velocity. And you can evaluate the kinetic energy of the initial system and the final system after collision, and you will see the kinetic energies are not equal in this case. So these are some sample problems. Now let us look at a case where the collision happens in 2 dimensions. For example, a particle comes in and collides with another particle, and the scattering is just not in 1D. The two particles after collision move at some angles, θ1 and θ2 as shown in this figure. So in this case, you can also apply momentum conservation, but remember, momentum is a vector quantity, so you can resolve momentum into the x and y components, 2 components, and you can apply the momentum conservation law along each of these axes independently. For example, because there is no force acting either in the x or in the y direction, you can write down the initial and final momentum along the y direction, and also write down the initial and final momentum along x direction, and you get 2 equations from which you can solve the quantities the problem is asking for. So you will see a lot of these problems in the tutorials and assignments and throughout your physics coursework.